start with state transition matrix part 2. So, computation of state transition matrix using diagonalization method. For any control system application, modeling, then state transition matrix, state equations, controllability, observability, control design, observer design, these are very important, particularly in advanced control system, advanced linear control system, these are very important issues. So, in all these issues we will find that diagonalization is a method which is useful in a modeling, it is useful in a state transition matrix, it is useful in controllability, observability, and even it is useful in a controller design. Therefore, this diagonalization has wide applications. Now, today we are discussing the how to use this diagonalization concept for getting the state transition matrix. Earlier we have seen how to determine the state transition matrix using power series method and also by Laplace approach, Laplace transform approach. Now, we will see how to determine the state transition matrix using diagonalization method. So, we start with the same state space equation. So, your state space equation is same x dot equal to a x, x naught equal to x 0, and here x of t to e raised to a t into x naught. Our purpose is to determine the e raised to a t by means of diagonalizations. So, diagonalization we have seen that it is based on the some additional state or different state, that means original system, let us say in a state x, it can be converted into state z or it can be converted into state k, any state. So, here our system it is in state x form, diagonalization means that it has to convert into different state. So, here first of all we assume this matrix A has distinct eigenvalues, that is eigenvalues are not repeated, that means we assume that the eigenvalues of A, eigenvalues of matrix A are distinct, that is eigenvalues of A are say lambda 1, lambda 2, lambda 3 up to say lambda n, these are eigenvalues, they are different. And as I told you that diagonalization is based on new state vectors. So, what we are assuming here a new state vector, let us say k. So, we can write down a state equation, let us say in terms of x equals to m into say k. X is the original state vector, k is a new state vector, and this m is a model matrix, which also belong to n cross n matrix. Now, we have to move further, we want equation in terms of k. So, what we will write from this equation, this k equal to m inverse x, k equal to m inverse x. Now, after this we can differentiate this equation, k dot equal to m inverse x dot. Now, this m inverse, what is x dot? X dot equals to x, so we can write down a into x, that is m inverse a into x. Now, what is x? This x is nothing but m k. Now, here our state it is in terms of k in the left hand side. So, in the right hand side also we should get the equation in terms of k. So, therefore, m inverse a and this x is replaced by m into k. So, if we can write this as m inverse a into m into k, and this nothing but k dot equals to m inverse a m into k, this is equations, and now this m inverse a m, this equation it is in diagonal form, that is k dot equals to a bar into k. where this A bar involve the eigenvalues lambda 1, lambda 2 and up to lambda n, that is in diagonal form. Diagonal form we have seen the elements are very less, only diagonal elements are present, remaining elements are 0. Now, our main purpose is to get e raised to at. We have reached into new state vector, but we have to reach to e raised to at. How will you move to it? So, now we have got this one, just like x dot equals to x, we have determined x of t. So, here also because equation in terms of k dot equals to a bar into k, we can get k of t, but question is remaining e raised to at. Now, we will correlate afterwards k of t and e of at. Now, in this particular case, a bar, as I told earlier, this a bar is nothing but this involvement of eigenvalues lambda 1, lambda 2 up to say lambda n. And I am writing down this equation again, that is k dot equal to a bar into k. So, as I told x dot equal to x, we are writing down x of t equal to e raised to at into x naught. Similarly, here also we can write down as k of t equal to e raised to a bar t into k into not k not k of t equal to a bar t equal to k into 0. Now, what is a e, what is a bar t? So, this we can write down in power series expansion as I plus a bar t plus a bars factorial 2 t square plus 1 by factorial 3 a cube t cube, like this. Now, this equation can be written as 1 0 0, say 0 1 0, say 0 0 1, like this, plus these equations a bar. What is a bar? A bar is your lambda 1, lambda 2, lambda n. So, we replace this here lambda 1, lambda 2 up to lambda n, that is into t, plus now here a bar square that means lambda 1, lambda 2, lambda n, that is we have to make square of these elements. So, we will get lambda 1 square, lambda 2 square to say lambda n square into t square plus 1 plus factorial 3 equals to lambda 1 cube, lambda 2 cube up to say lambda n cube into t cube. So, this we have done. Now, we can add the elements of each rows and see what result we will get. So, if you add these elements, you will get 1 plus lambda 1 into t plus 1 plus factorial 2 lambda 1 square into t square plus 1 plus factorial 3 lambda 1 cube into t cube, and you will find that all the elements are 0. Now, coming to the second row, in this second elements in the second row, we will get the elements at 1 plus lambda 2 t plus 1 plus factorial 2 lambda 2 square t square plus 1 plus factorial 3 lambda 2 cube t cube, and rest of the elements 0. That means, in the second row, in the second element we have element means variables, but rest of the elements are zeros. Second element, rest of the element is 0. Now, this process repeated, and at the last row last row, last column, you will get the elements as 1 plus lambda n t plus 1 by factorial 2 lambda n square into t square plus 1 plus factorial 3 lambda n cube into t cube. That means, if it replaced properly, we can show like this. This is T1, T2 and up to your Tn, and here this T1 is nothing but this part, this T2 is nothing but like this, and Tn like this, that is Tn here 1 plus lambda n t plus 1 plus factorial 2 lambda n square t square plus 1 plus factorial 3 lambda n cube into t cube. This process we did. That means, we will get elements in the diagonal form only. Now, what to do further? Now, this we can replace in terms of lambda 1, this we can replace in terms of lambda 2, and this we can represent as lambda n. That means, finally, this equation, that is e raised to a bar t can be written as e raised to lambda 1 t, e raised to lambda 2 t up to e raised to lambda 1 into t. That means, we are starting with this a bar k into a bar k, we got a bar t, we have got these results and we have added. After addition, we have got this, and this particular part written as e raised to lambda 1 t, this e raised to lambda 2 t, e raised to lambda n t, but our main purpose again is e raised to a t, but now we are raised to a bar t. Now, how will you get it? Now, here x of t equal to m into k of t. Just see here x m k, that is x of t equals to m k of t, and as I told you that after doing all this adjustment, we have reached to e raised to a bar t, but our concern with the x of t. So, here this is m, and what is k of t? This k of t equals to e a bar t into k of 0. You see here, this k of t equal to a bar t into k of 0. See here, we have replaced m e raised to a bar t into x of k of 0. Now here x equals to m into k. That means, if you write x of 0 equal to m k of 0, that means k of 0 equal to m inverse into x of 0. So, here we replace this x of 0 equals to m inverse into x of 0. So, we can write down as m e a bar t equal to m inverse x into 0, that means x of t m e a bar t m inverse into x of 0, and we know that this x of t equal to e raised to a t into x naught. So, if you compare this equation, we can get equal to m e a bar t into m inverse, we will get m inverse. So, e of t equals to m e raised to a bar t into m inverse. So, this is the method of getting the state transition matrix e raised to a t, and this e a bar t can be written as e lambda 1 t, e lambda 2 t and e lambda 1 t, that is m inverse. So, now this methodology we have seen, and we will find that as mathematical portion it is quite cumbersome, But then question has been come, why in a practice we will do all these type of calculations, because today we have softwares and we can easily get these results. After we will see how to calculate this state transition matrix using some MATLAB software, but question has been come, what is the importance of this in today's time? In today's time, if you consider with some numerical parameters, numerical values, then there is no use of such methods. Only from academic point of view, for getting some result it is useful. But if you are working on some practical problems, what are the correlations between different states, what are the eigenvalues corresponding to these states, so that internal information we can get by this one. That type of information can be achieved by means of software. Therefore, this has method, if you see from research angle, is quite useful. Now, we will try to solve some example based on this approach. Let us say a given matrix A is written as -2 1 3 0 -3 0 0 5 -1. This is the matrix A, and our main purpose is to determine e raised to at. This is it, and we have to use this diagonalization approach, and we have already seen the formula, and then we will try to determine e raised to at. As in this particular approach, we will find that it based on the model matrix M, and how to get the model matrix. The model matrix depends upon the eigenvalues and also the eigenvector. Therefore, whenever the problem has come to you, and if you want to determine e raised to at by diagonalization, the first step we have to calculate the eigenvalues of this matrix. So, the eigenvalues of this matrix, if you calculate it, the eigenvalues of this matrix A, eigenvalues of matrix A, lambda 1 equal to -1, lambda 2 equal to -2, and this lambda 3 equals to -3. These are 3 eigenvalues. So, to get the M, we not only require eigenvalues, we also require the eigenvectors, and we have seen last time that if a given system matrix A, it is in companion form, that is, or controllable canonical form, that is A equals to 0 1 0 0 0 1 -2 -3 -4. If this is the case, we have seen that the model matrix M can be determined as 1 1 1, lambda 1, lambda 2, lambda 3, lambda 1 square, lambda 2 square, lambda 3 square. That is called van der Monde matrix. That is, eigenvector can easily be represented. But when a general matrix is there, because you see that this matrix is general matrix, we cannot know what is the property of this matrix just looking after this A matrix. Therefore, in that such case, we have to actually calculate the eigenvectors. So, if you calculate the eigenvectors of this matrix A, eigenvectors of each eigenvalues, you will get for eigenvectors for lambda 1 equals to -1, we will get 3 0 1. The eigenvectors for lambda 2 equals to -2, 1 0 0, that is eigenvector for lambda 2 equals to -2, 1 0 0, and third lambda 3 equals to -3, the eigenvectors are -13, -2, and this is 5. Now, these are the eigenvectors for each eigenvalues, and to get the model matrix we have to combine these eigenvectors. So, the eigenvectors we have combined, we will get the model matrix, and this M equal to 3 1 -13 0 0 -2 1 0 5. So, we have got M, but now if you see the formula, M e raised to a bar t into M inverse. M we have calculated, as I told, by eigenvectors and eigenvalues. Now, to get the M inverse, this is also quite troublesome work, and you say that as the order increases, quite difficult. Even for third order also, if you do it, it will take at least 10 minutes. But the simple method I already explained, the Levy algorithm, where there is no need for calculating the determinant. Based on the trace of the matrix we can also get it. Now here if you calculate the inverse of this matrix M, so we will get M inverse we will get it as 0, 2.5, 1, 1, minus 14, minus 3, 0, minus 0.5 and 0. So, we have got M inverse. The next step we have to determine this E a bar into t, e raised to a bar into t, that to be determined. So, now e raised to a bar t and this e raised to a bar t is depend upon the eigenvalues. That means in the diagonal element or in the diagonal rows, we can say we have to write the element in terms of eigenvalues. So, the eigenvalues are minus 1, minus 2 and minus 3. So, here we can write down as e raised to minus t, e raised to minus 2t, e raised to minus 3t and rest of the elements are zeros. So, we have got M, we have got M inverse, we have got E a bar into t, and what is the final stage? Your final state is e raised to a into t, that is M E a bar t into M inverse. So, now if you multiply all these 3 matrices, you will get the result as, that is e raised to a into t, that is M e raised to a bar t into M inverse, that is equal to e raised to minus 2t, 7.5 to e raised to minus t plus e raised to minus 2t plus 6.5 into e raised to minus 3t, then here 3 into e raised to minus t minus 3 e raised to minus 2t, here we get 0, here we will get e raised to minus 3t, here we will get 0, then third row 0, 2.5 into e raised to minus t minus 2.5 e raised to minus 3t and here e raised to minus t. So, this is nothing but a state transition matrix using a diagonal method or we can say a canonical method, diagonal canonical form of method. And again, as you see, calculation wise is quite cumbersome. Therefore, as I told earlier, we better to go for the Laplace transform, but sometimes we have to go for some internal analysis. This method is quite useful. This method, as I told, it is useful for state transition matrix, also state equations in a model. We will find that this approach is also useful in a controller design. So, that part we will see when I will explain you how to design a state feedback controller. Now, these are some references: Dira Chaudhary, BC Ku, and also this Nagrath and Gopal. Thank you.